Okay, we still continue with our section 4.4. Let's look at normal curve approximation to the binomial sampling distribution. These bell-shaped sampling distributions kept occurring with amazing regularity in coin and dice experiments when our sample size, number of coins, and or dice dropped was sufficiently large. What do we mean by sufficiently large? In these types of sampling experiments, known as binomial sampling experiments, if expected value, sample size times the proportion, is greater than 5, and sample size times the 1 minus proportion value is greater than 5, the sampling distribution, which is known as binomial sampling distribution, will be approximately normally distributed, with mean n times p and standard deviation square root of n times p times 1 minus p. And a normal curve with these dimensions can be fitted over the distribution and used to estimate probabilities. Now, let's look at an example to see how this works. Here the same example. Out of 12 tosses of a coin, find the probability of achieving exactly 6 heads. Our expected value calculation is n times p is going to give us 12 times 1 half, which is 6, which is greater than 5, and n times 1 minus p, which is 12 times 1 minus 1 half, which is also equal to 6 and greater than 5, which is satisfying our conditions. Our expected value is greater than 5 and n times 1 minus p is greater than 5. Now, no repeated samples of 12 will produce a sampling distribution approximately normally distributed, such that a normal curve with mean and standard deviation can be calculated with the formula n times p, which we get already 6 heads, and the standard deviation square root of n times p times 1 minus p. N is 12, p is 1 half, 1 minus p in this case is going to be also 1 half. When we do this calculation and put it on our calculator, we get 1.73. Now let's go back to our question. We still continue with the same question, but we didn't answer the last part. What about the probability of achieving exactly 6 heads? So in order to do that on our histogram, we are going to shade the bar representing exactly 6 heads. As you might remember from the first lectures, when we do the histogram, we are going to do a width from 5.5 to 6.5. And this half point adjustment is going to include the parts over here, 6 heads. And on the right side, you can see we resketch the same part, same graph, with only the 6 heads part, and are now borders are 5, x value is 5.5 on the left side. On the right side is 6.5. What we need to do is we have to find the z-score values for 5.5 and 6.5. In order to do that, we need our formula. Z is equal to x minus mu divided by sigma, which means x, our data value, 5.5, minus mu, our mu in this case is 6, divided by sigma, which is found earlier, which was 1.73. When we do our calculations, we will get, for the 5.5, we will get 5.5 minus 6 divided by 1.73. We get negative 0.29. The percentage of data from z is equal to 0 to z equal to 0.29, negative 0.29, is 11.41%. So you might wonder how I got 11.41%. After I find the z-score, which is negative 0.29, when you look at 0.2 and 0.09, where these two values intersect is here, 0.1141, which is the area between 0 to 0.29. So we see that the area between negative 0.29 and 0 is equal to 11.41%. And we know that in normally distributed graphs, the area is, this shaded area is symmetrical. So this is half the data, half the area is 11.41%, and the other half of this rectangle is going to be also 11.41%, which is going to result 22.82% for the whole area of this this part of the histogram. Since there's an equal amount of data from z is equal to 0 to 0.29, we added, as you can see over here also, calculation, and we get 22.82%. Now, this is answering our question of probability of achieving exactly 6 heads is equal to 22.82%.